Okay.
Okay, thank you. So, in some sense, this is very closely related to the previous talk. In a much more restricted setting of linear groups, we aim at rather good, better bounds. So let me recall the result that Emmanuel very briefly referred to. So there is this product theorem for, let's just state it for SL and Q, which was proved independently announced the same day in 2010. And this is the following. If we have a generating subset of SL and Q, then either a to the third is everything, or a to the third is much larger. Epsilon is a constant which depends on the n, much larger than a. Both proofs extend to simple groups of Lie type of bounded rank. Ours is rather harder to read, but as Tao commented on his blog, it's related perhaps that it's effective in a certain sense. Okay. As many of you may know, such a result, that was the real breakthrough, was first proved by Harald Helfgott for SL2P, and then in major work he extended to SL3P, and Deny and Varyu proved for SL2Q, similar kind of result. So the SL2P result had lots of applications to expanders that you will hear about in, for example, in Gambor's talks and in other talks. And therefore, it was really desirable to extend it in general. And the fact that there is a separate paper for SL3 shows that it's maybe not obvious. So let me mention some applications in a to show why it's important or interesting. So there is an old conjecture of Laci Babai that Ákos Seres will talk more about. And this is the following. Take a finite non-abelian simple group and take any Cayley graph, connected Cayley graph. Then the diameter should be polylogarithmic in an absolute sense. That's a still open, very old conjecture. The first case that was settled was done by Helfgott using his theorem, actually. A second conjecture, which is rather more recent, is due to Liebeck, Nikolov, and Shalev. Take any subset which is of size at least 2 of a non-abelian finite simple group, L. Then L is a product of log L divided by log S copies of conjugates of this set. So this is obviously sharp, and actually when S is a conjugate, S cannot be conjugated, so when it's a normal subset or a conjugacy class, then it's a very deep theorem already of Liebeck and Shalev, which has many applications. So this is a generalization to arbitrary subsets. So this is a conjecture, a recent conjecture. And there, what? Yeah, it could be a subgroup. And then you have to conjugate. No, we don't assume generation. An arbitrary subset, we don't assume that it generates the group. It could be a subgroup. Actually, it was a previous conjecture that it holds for subgroups. And this is still open. So it's different in this respect. Okay? So probably in Jerusalem, I don't have to define, I still do, that a graph is an epsilon expander if for all not too large subsets, the neighborhood of A in the graph So the is at least epsilon times A. So this is an expander graph, and there is a conjecture or problem, I never know what, maybe Alex can tell me, of Lubotsky, that if we have two random elements in a non-abelian finite simple group, then the corresponding Cayley graph is an epsilon expander with probability going to 1. What is it? Conjecture? Problem. In your survey it's a problem, somewhere else. Whatever.
Well, if you will solve it for an, whatever the answer will be for an.
Then it will be a, yes, good answer. Okay, politician's answer. Sorry. Okay. It's already a deep theorem. Dixon, Cantor, Lubotsky, Liebeck, and Shalev proved parts of it, that the graph is connected. So two random elements generate a non-abelian finite simple group. So this is that puts this into perspective. So to do something really nasty, I think I should say that there's this statement, all these are true for Lie type of bounded rank and widely open in general. So why is it a nasty kind of statement? Because the diameter conjecture, Boboi's conjecture, is a direct corollary of the product theorem. This product decomposition conjecture with the conjugates is due to Gill, myself, Short, and Szabo. But actually, it's a you use the product theorem, and you need an extra trick for small subsets. So it's a short proof, a little bit more tricky than obvious. And for expanders, this is a deep result of Breuer, Green, Guralnik, and Tao that you will hear about, I think, by Guralnik this week. Okay? But the point is that there are a number of conjectures where the product theorem does everything for bounded Lie rank. So, for example, you don't have to care about exceptional groups and all others. And these are similar in this respect. And they are similar, the applications are similar in a different respect, that in all these proofs, it is essential that the product theorem is in a polynomial type theorem. So it means that in the theorem, which I will not pull back, we have a generating set. If A, let K be the tripling constant, a to the third divided by size of A, then the product theorem basically says that A has size at most this tripling constant to a constant number, so it has polynomial size, unless it's very large. The main thing is that between the growth and the set size, there's a polynomial relationship. And this is essential in all these three applications. And there are more. I think Gambord will talk about more, but somehow that's, I think, enough for now. So what I'm trying to say is it's really well worth to get good bounds in this context. So, so the general question, so we had a result for simple groups. And in the end, I want to tell you that it has nothing to do with simple groups. So which sets do not grow in linear groups? So this is very similar to the approximate group stuff. This is a problem that is somehow it's coming from various remarks of and discussions by Helfgott, Breuer, Green, Tao, Tao's blog, blah, blah, blah. Unfortunately, it has never been explicitly formulated that that's what someone wants. Nevertheless, that's what we try to do. We want to characterize sets which do not grow, or at least get information, in the sense that the constant, the relationship between the growth constant and the structure should be polynomial, so that we should preserve this feature of the product theorem. So that an experimental first thing in our first long manuscript was a polynomial inverse theorem, in the sense that there's a polynomial Feynman-Ruja conjecture for a sharp polynomial version is expected to hold for instead of Feynman's theorem. But I will not define this. So we have a polynomial inverse theorem, which is the following. If we have a subset of SLNP, so the easiest case in some sense, fields of prime order, a symmetric subset such that it satisfies s to the third less than k times s. So k is the tripling constant. Then, and I will give you a picture also, there are subgroups H and P such that P, the small group, is essentially contained in my original set. It is contained in s to the 6. And the large group essentially contains my set so that polynomially many cosets contain. I have a very clever drawing of this situation which may help to digest this. So if I have a non-growing set, this green one, then S to the 6 contains this subgroup P, which is a finite perfect subgroup. Here we have a big group. In between, we have something soluble. That's the crucial thing. Here it's finite, soluble, and a few cosets. So it gives some kind of a structure of how a non-growing subset of a linear group can look like. And this uses results of Nori and already has applications in some algebraic geometric applications, which the original product theorem does not have. So the point is that somehow we managed to reduce the question of determining with polynomial constants these non-growing sets to the soluble case. That's one interpretation. Now, how to go on from here? So that was a preliminary result. You can have more precise results. You can perhaps show that this part is nilpotent. This was done by Gill and Helfgott in this case. Or you can have a more Okay, so the picture is that I have this green non-growing set. Then I have a finite perfect group, which is essentially contained in S. So S to the 6 contains this. So it's basically there. And then I have here a big soluble infinite group on top. And this finite by soluble basically contains my green set. There are only polynomially cosets that all together cover. So the structure is somehow captured by these subgroups. That's what I'm trying to say. And so already Aner was asking me what's the difference between a talk I gave last year in Wales. In Wales I mentioned that we could extend it to arbitrary finite fields, basically using some finite group theories somehow. But it's very different because Nori's result does not extend that we use here. And let's go on to arbitrary fields, infinite fields. So Breyer, Green, and Tao in 2010 already proved that in characteristic 0, which of course does not contain the SLNQ, SLNP case, which is related to the product theorem. So it's a different case. If you have a non-growing subset, then it's contained by polynomially many cosets of a soluble subgroup. In this case, there's no finite subgroup. And by earlier work of Breyer and Green, here you can say that this soluble subgroup is nilpotent. The proof uses a fact that's true in characteristic 0 and not true otherwise, that a soluble group, virtually soluble group, has a bounded index soluble subgroup. oops. And another step we did have is for arbitrary fields. If you have a non-growing set, then S can be covered by polynomially many cosets, basically of a virtually soluble subgroup. So that's information for arbitrary fields. You can strengthen it, and actually a similar result was obtained by Khrushchevsky. So, but the constants in his case are not explicit and not polynomial, but some function. I tried to convince you at the beginning that polynomial is nice, and this is the thing that gives applications, that certain kind of applications, I should say. So the result that we had was a polynomial version of Khrushchevsky's result in some sense. And finally, we somehow managed to complete this and show that this polynomial inverse theorem holds for arbitrary fields. And one reason why I mentioned the previous special cases is that actually these combine, this can be combined to give the final statement. So just to remind people, so again, this means that over arbitrary fields, if s to the third is less than k times s, then we have a finite perfect subgroup and a soluble group, I called it H, such that P is contained in s to the 6, very close. H over P is soluble, and we are contained in polynomially many cosets of this. So the reason why I think it is interesting, at least, that if this subset happens to be a generating set of SL and Q, then this statement basically reduces to the product theorem. So we have a theorem which is not about simple groups, arbitrary subsets of linear groups, but which contains. I should say that, at least for us technically, the product theorem was sort of halfway. So the proof does use all the previous special cases. So this is a general theorem for non-growing subsets. Okay. And here I mentioned that, of course, Breuer, Green, and Tao had this wonderful, very general theorem for arbitrary subsets of arbitrary groups which don't grow, but where you don't have good bounds, which hopefully will lead, which leads to different kind of applications, I should say.
Can one require that H over P is nilpotent?
Yeah, as you just asked this. So there is a task, as Tao also suggested, to suggest that it's a finite by nilpotent. Instead of finite by soluble, which essentially covers my set, there should be a finite by nilpotent. Although it may be that there you use some conditions, like I can assume here among the conditions that H and P are normalized by my original subset. And this will be very hard to maintain if you reduce to nilpotent. It's a lot of extra work. And if you don't have this, then the product theorem will not be a special case. So, but maybe it can be done, but it will be, I think, to have both, to have nilpotent and all these conditions, may be very hard. For SLNP, it was done by, I told it to Harald Helfgott, and they did it in an extra 10 pages. But in SLNP, you don't have so many possibilities. So it's possible, I don't know. Of course, you can go on. But so that's a task which we may or may not try to do, but it requires different techniques. Rather, I would mention something like a daydream, which is in a direction of sharpening the great result of Breuer, Green, and Tao. So the daydream is, okay, let's have a linear group over an arbitrary field and a subset which doesn't grow in this sense. Then is it true that S is covered by absolute polynomially many cosets of a nice subgroup, and I allow you to have a virtually soluble subgroup with no other restrictions. So somehow it sweeps off. So you give me any finite or abelian or soluble examples, it doesn't care about these. So somehow if you want to break the problem, that should be an essential step. So so that I would suggest as a question. Actually, you can consider it in a more restricted sense for subsets of your favorite group. So it does certainly make sense to consider it for the Grigor-2 groups because they have something to do with growth. They have intermediate word growth. And it would be interesting to see that that kind of statement holds, whether that kind of statement holds for all subsets of such groups. Maybe there is a counterexample there. Okay, where the polynomial degree of the polynomial will depend, then will not be an absolute constant, but will depend on the group that we pick. What?
Day is the name of person or today?
No, it's not a name. I just mentioned your name. I know. No. I know. Yeah. Okay. Okay, some hints for the proofs. So I lectured about it too often, so eventually I just want to show why it's very natural to prove the product theorem. So why it's almost obvious that you should end up with this proof. So take SLN Q. It has q to the n square, order q to the n square minus 1. And if you take a maximal torus, it has order q to the n minus 1. And Helfgott, in his longish manuscript, has this very nice lemma that if you have a set which doesn't grow, a to the third has roughly order a, then the intersection with any torus is at most the size of a to the 1 over n plus 1. Basically the point that you can take a torus and conjugates by short elements so that they are roughly orthogonal to one another. And if you have many elements in one torus, more than this many, then you take this neighboring conjugate tori. There you still have similar number of elements. You take the product and, hey, you have too many, more than a, in a small power of a. But a small power means that you have too many elements in a to the third. This is Ruzsa-Plüneket estimates. Okay, but still, so this is the so there were many facts, but this is a very nice fact in Helfgott's paper, which one eventually says, okay, this is what we want to generalize. How do you generalize it? There are similar results for other subgroups. So what is the right generalization? For all tori, less than. Then it grows. No, I have this assumption. If a to the third, if it's inside T, then the set grows like hell. If the set does not grow, if a to the third is roughly of the size a, well, this is one of Helfgott's lemma. What? No, but in the group. A generates the group. A is a generating set. Okay. Well, certainly A cannot be completely inside the torus. Okay. So the first thing is, okay, this is the right result to generalize. What is the right generalization? Answer, which is a main tool in this particular proof of the product theorem, which is called by Breuer-Green-Tau Larsen-Pink type inequality. You take, as SLNQ is comfortably sitting in SLNFP, take a variety, and basically what you want to show is that A doesn't have too many points inside any given variety, where the too many means that A intersection V is less than A to the K, where K is some small number, divided by dim V over dim G. So, for example, when you have a torus, this gives back Helfgott's inequality. And I'm cheating because there are a lot of constants around which in the proof don't matter. Okay, so this is the right generalization, that instead of the tori you should, and other subgroups, you should consider it for varieties and their intersection with SLNQ. Okay, so this was the first question. What is the right generalization? Next question, what are the interesting choices? You have a general theorem. Do you get anything more than Helfgott did? What are the interesting choices? And the interesting choices are pairs of the centralizer of an element X and the conjugacy class, the closure of the conjugacy class. So these are nicely in pairs, and you can. And the point is that if you play with these, you can see that an upper bound, which is what we have. We only have upper bounds. The problem is we don't have lower bounds. But an upper bound for the intersection of A with a conjugacy class gives you a lower bound for the intersection with the centralizer. Therefore, for these subgroups, centralizer subgroups, you always have not just an upper bound, but a matching lower bound, if A doesn't grow. Okay. If T is a maximal torus, let's call TR be the regular semi-simple elements in T. So all eigenvalues distinct. So there is a dichotomy here. So if A does not grow again, then take the regular simple elements in any torus. If A does not intersect in a given torus this set, then the intersection of A and T is small. A to the n-2 over n squared minus 1. If the intersection of A with these regular semi-simple elements is non-trivial, then for a small power, AK intersection T is large. It can be called that these are the rich tori and the poor tori. So it's a welfare society because there's not such big difference. But still, n-2 is different from n-1. So there are two types of of these sets. Either you have many elements of A or not too many. And okay, so we have something balanced. And the next question, which makes it, how do we break this balanced distribution? What can you do? You can the only thing eventually you can do is you start conjugating. And basically, I think okay. So basically, I don't want to give the argument, but this balanced distribution cannot be invariant under conjugation, and that ends somehow the proof. So. So, as I told you, the first step towards a general result for linear groups was basically that we could localize the set, the non-growing set, within a virtually soluble group. And for this, you have to generalize this Larsen-Pink stuff, and instead of tori, you have to establish a more general set of, you have to consider a more general set of centralizer subgroups. So there's a mini theory of that, and you can generalize the whole proof, and in the end you get a tool which by induction gives you that a non-growing set is contained in a virtually soluble group. So what I'm saying is, here the main thing is to find the replacement for the tori. And the same kind of proof works.
Is the replacement for the tori?
Connected centralizers of connected subgroups appropriately chosen. And somehow they have you can establish one by one the properties which are needed for the proof. Not all properties of the tori. They will be the centralizers of at most d points always. So somehow it will be very similar. Okay, so this is about how we get for non-growing sets of linear groups that they are located in something virtually soluble. So how do you get SLNQ? You have to use the product theorem and many finite group theoretic tricks. In particular, you can use the result of first stated explicitly in a paper by Nikolai and myself, that if you have, it's a very useful lemma, so you use it, iterate, and it just kills obstacles. So if you have a subset of a group which is larger than the order of the group divided by k to the 1/3, k the minimal degree of a complex representation, then a to the 3rd equals g. One example of an application, if we have a non-growing set somewhere in a group, I'm not talking about linear anything, somewhere in a group, G, which is normal in N, assume that N is contained in a to the k, and assume that N has large minimal complex degree, then actually N is contained in a to the 6. So under this condition, containment in a to the k goes down to a to the 6. So it means that if you have a weak version of this containment, you have a strong version. That's one easy application of this Gauss trick. But there are many others, so it's mainly finite group theory, which does everything for SLNQ. And I promise that these previous cases give you the final result. So if we have a non-growing subset of SL and F, we already know that it's in polynomially many cosets of virtually soluble G. And we know for finite linear groups the result. And there we use the residual method, which is based on a result of Maltsev, that if we have a finitely generated subgroup of GL and F, say in characteristic P, the characteristic 0 case was done earlier, then for every finite number of elements, say T elements, there is a finite field of order P to the alpha, same characteristic, and the homomorphism that the images of G1, Gt are different elements in this finite linear group. So this is a classical result of Maltsev, and that somehow indicates how you can combine this virtually soluble result and the result for SL and Q. It has to work out, and it's not obvious beforehand that it works out, but actually you really have to use these two together, and then you get this inverse theorem, polynomial inverse theorem for arbitrary fields. Okay, thank you.